Hi guys, in this video we're going to revise analytical chemistry for AS. Quiet. And the past paper question pack used in this video can be found by clicking on the link down below in the description. This first question, which statement about absorption of radiation is correct? We've got four statements. The first one says absorption of infrared radiation can break covalent bonds forming radicals. That is not true. That's only true for ultraviolet radiation. Then B, absorption of infrared radiation causes covalent bonds to vibrate more. That is true. So the answer is B. This next question, the mass spectrum of a carboxylic acid contains peaks at MZ, so that means mass to charge ratio. It's the numbers on the x-axis on the mass spectrum. So at MZ 29 and MZ 102, which compound could have produced the spectrum? So we need to translate in our heads, if you like, these skeletal formulae into displayed. So at each point there's a carbon, there's a CH3 here, we just don't show the hydrogens, CH, another CH3, this is a CH2, a carbon, and here's the carboxylic acid group. So when a compound is in a mass spectrometer, it fragments and it breaks into fragment ions, and any one of these bonds can break. So this peak at MZ29, that is a fragment of this molecule. And it's quite a common fragment, and it's indicative of a CH3CH2, so an ethyl group. So the question's asking which one of these four carboxylic acids contains both a peak at 29 and 102. So 102, that's quite a big value. So the first thing I did was to calculate the molar mass of these four compounds. And some of these have a molar mass of 102. So it rules out B and D. It can't be those. And the next thing, I figured out that this peak at 29 must be an ethyl, or it's likely to be an ethyl group, because carbon is 12 on the periodic table, hydrogen is 1, so we've got 12 plus 3 plus another 12 plus 2 gives 29. So we've got an ethyl here, but not on this one. So the correct answer is C. This next one is about infrared spectroscopy, and it says which compound could have produced the infrared spectrum above. So the first thing we do is to look in our data sheets at the characteristic infrared absorptions table here and try and identify some of these absorptions on the left hand side. So anything below 1500-ish is called the fingerprint region, and we normally just ignore that. So this absorption here in this range is characteristic of an OH absorption. And if we look at our data sheet, it's in the range 3200 to 3600, which it matches on here. There's also an absorption for OH for carboxylic acids, which is in this table, 2500 to 3300. And if we look on here, this is outside of that range, and it's not quite broad enough to be a carboxylic acid. So this is an OH of an alcohol. We have another significant absorption here around 1700-ish, and that is characteristic of a carbonyl, a carbon double bonded to an oxygen, which is present in aldehydes and ketones. So we've got two absorptions of two bonds that together look like they make the carboxylic acid functional group. However, this OH absorption was not in the range, not quite in the range for a carboxylic acid, and it's not broad enough. So that suggests two different functional groups in the same molecule, an alcohol and an aldehyde or a ketone. So that agrees with compound B. This question is about mass spectrometry and relative abundance, and we have a mass spectrum of two different isotopes of chlorine, and we have a relative abundance, so a percentage, and a mass number or mass to charge ratio of both. And all we do is times the relative abundance by the mass number, the mass charge ratio, add them together and divide by 100 because it's a percentage. And it wants the answer to 2 decimal places. And we should get a number in between these two. And we get 35.48, which makes sense because it should be closer to the mass number of the isotope with the higher relative abundance. Part 2 of this question says the mass spectrum of chlorine also contains 3 molecular ion peaks. One of these M+ peaks has an MZ value of 72. Suggest why an M+ peak, that's the molecular ion, which is equal to the molar mass of a compound. So suggest why a peak is observed at 72 and predict the MZ values of the other 2 M+ peaks. So we have a peak MZ72 because the sample contains both isotopes of chlorine, chlorine 35 and 37. And this means we have MZ values of 70 because 35 times 2, chlorine is diatomic, gives 70, and 37 times 2, that gives 74. On this one we have an infrared spectrum for a halogenoalkane and it's labelled the carbon-halogen bond. And that's quite helpful because these carbon-halogen bond absorptions appear in what's called the fingerprint region, which we're often told not to label. So that's anything approximately below 1500 we're told not to label, unless we have a halogen. Then it says outline how infrared spectroscopy could be used to show that the bromoalkane functional group has reacted and that the alcohol functional group has formed. So if the bromoalkane functional group has reacted, then we'd expect this absorption here to disappear. So we can say disappearance of the carbon-bromine peak at, and then quote the wave number from our table in our data sheet. And when the alcohol functional group forms, we can just say we expect an OH alcohol absorption to appear, and we just quote the wave number from the data sheet. This next question says compound F is a trans stereoisomer. So when we have cis and trans, that indicates an alkene, so at least one carbon-carbon double bond. And it gives us results of elemental, so percentage composition, and spectral analysis, infrared and mass spec. So a good place to start is with the percentage composition data. We can treat these percentages like masses in grams. And to do empirical formulae, the first step is to calculate moles. So treat these like masses. We do mass over mass number from the periodic table. We get a value. And then we divide by the smallest. So this is the smallest out of these 3 numbers. So we divide all 3 numbers by 1.43. And we get 4 for carbon, 6 for hydrogen, 1 for oxygen. So that's our ratio. Then we convert that into an empirical formula by putting the element symbols in, C4H6O. We can work out the molar mass of this empirical formula and see if it matches our molecular ion, which gives us molar mass from the mass spectrum. If it does, that means that the empirical formula is also the molecular formula. Now we can look at our infrared spectrum. And we can see we have a carbonyl, a carbon double bonded to an oxygen absorption, which indicates a ketone or an aldehyde functional group. Now, before we look back at the mass spectrum, it probably would have been useful if I showed you the rest of the question. It says, in the mass spectrum, the peak with the greatest relative intensity is caused by loss of a functional group from the molecular ion. So the functional groups are things like aldehydes, ketones, carboxylic acids. From the infrared, we suspect a ketone or aldehyde. Can't be a carboxylic acid. We've got no OH absorption here. So if we do the molecular ion, which is the molar mass of the whole compound, minus the mass number of this most common fragment ion here, we get the mass of a functional group. And 29, that is equivalent to 1 carbon, which adds to 12, 1 hydrogen, which is 1, and 1 oxygen. So that's consistent with an aldehyde. Then we're asked to determine the structure and explain our reasoning. Now I've done my notes all on the previous page, but I've put them on here as well to show you where we get the marks. And this is levelled marking, so it's not like there's one mark for each point. It's got different bands, and I can link the mark scheme in the description below so you can have a proper look at that. So here's a summary of the key points from the previous page. The empirical formula, we found that from the percentage composition data, it's C4H6O. From the infrared, we found a carbonyl, carbon double bonded to oxygen absorption in this range. From the mass spec, we got the molecular ion, which gives us the molar mass of the compound. The empirical formula's molar mass was also 70, which says that the empirical formula is also the molecular or the actual formula. It's a trans stereoisomer, so we've got an alkene, a carbon-carbon double bond present, and our most common fragment ion is from loss of a functional group, which tells us that it's an aldehyde. On this next question, we've got 6 different alcohols and we've got skeletal structures for these. The question says that compound X is one of these 6 alcohols. A student refluxes compound X with acidified potassium dichromate as an oxidizing agent. A pure sample of the product Y is obtained. The mass spectrum and infrared of Y are shown below. So this is like a problem-solving question. If we look at the infrared first, we can see there's no OH peak, so it's not an alcohol, it has reacted. But the absence of an OH absorption also tells us that it's not a carboxylic acid either. So if we're refluxing and we haven't had a carboxylic acid formed, that means we've had a ketone formed, and ketones are formed from secondary alcohols. So we label our ketone peak here around 1720. And then we want to identify which of these alcohols are secondary. And it's these 3 here, C, E and F. If we look at our mass spectrum, we can see the molecular ion is 86. That is the molar mass of the alcohol. So we can also look at the molar masses of these and see which ones of these secondary alcohols also add to 86. Looking at the most common fragment ion, that gives us information about the structure. So 43, that is equal to a CH3, a CH and another CH3, and that is only consistent with alcohol E. This question's also levelled marking. So I've written some summary points of the notes and the annotations from the previous page to show you everything you need to include to get the marks, and I'll link the mark scheme for this down below as well. So it wants us to identify compound X and product Y and write an equation for formation of product Y from compound X. So we identified our carbonyl absorption at 1700. Reflux suggests a ketone and not an aldehyde. The infrared had no OH absorption, so it can't be a carboxylic acid. From the mass spec, we identified the molecular ion at 86, which is also the molar mass, and the most common fragment at 43, which could be either C3H7 or CH3CO. So I wrote it slightly differently here, but that is also C3H7. It's the same. And then to form a ketone, X must be a secondary alcohol, and compound E is a secondary alcohol that fits with the fragmentation pattern from the mass spectrum. And here's our equation. So we've got our secondary alcohol reacting with oxidizing agent to produce the ketone and water. Last question, it's another combined analysis one again. So we've got a mass spectrum and infrared, and that's all. So this one's from a breadth paper. It says a compound E contains carbon, hydrogen and oxygen only. and we've got a mass spectrum and infrared. First thing we look at, we identify the molecular ion, which gives us the molar mass. It's 88. Most common fragment ion, it's always a good idea to identify this or to try and identify what it could be. 43, that adds to CH3, CH2, CH2 or a propyl fragment. And this peak here at 45 could be a Cu, so a carboxylic acid group. But we won't know until we look at the infrared. On the infrared we can see we've got a carbonyl absorption here around 1720-ish. We've also got a broad OH absorption, and this is definitely suggesting that it could be a carboxylic acid now. We don't have much more information to go on, so the next thing we can do is use our molar mass and subtract the mass of the carboxylic acid functional group from this to find out how long our carbon chain is. So 88 minus 45, we end up with 43, and that adds up to a combination of carbon and hydrogens. So 3 carbons and 7 hydrogens. So it's likely to be butanoic acid. The question's asking us for 2 possible structures for this compound. Butanoic acid and a branched isomer of this, 2-methyl propanoic acid. And here's where we get the marks. Identifying the molar mass from the molecular ion on the mass spectrum, identifying the carbonyl absorption on the infrared, along with the carboxylic acid OH absorption, and 1 mark for each possible structure.